for ultrasound, and it is truthfully about 60% of the registry exam for the SPI physics. So if you can take this drawing and recreate it when you get in there to take the exam, then you'll get at least 60% of the questions correct. It is very fundamental to almost everything they ask. So there's a lot more that goes on it than just the two waves and a couple of arrows, and we'll be filling it out here as we go, so we can learn about it. So I want to start out today talking about transducers. Transducers, they listed as 30% of the exam, so you do have to know a lot about them. And today we're specifically going to talk about the single crystal transducers, which are the kind that are found on this machine. I've called it the Triceratops. So it's an older machine, but it is obviously very valid, the information that you get from it. The crystals in it, each probe, each of these little sector probes that it has a single crystal that's in there that wobbles back and forth and takes pictures, and we'll get into what that is. So what is a transducer? It's anything that converts one type of energy to another type of energy. Nerves are types of transducers. Lights are transducers. They convert electrical energy into light. Speakers are transducers. They convert electrical energy into sound. Heaters are transducers. They're converting electrical energy into heat. Microphones are transducers. They convert sound into electrical energy. So there's a lot of different transducers that are out there. You can think of many that I haven't mentioned, and they're all valid transducers. The ones that we use in ultrasound are generally speakers and microphones. Okay, we use a speaker to send out a pulse of sound into the body. We use a microphone to listen to the echoes that come back from the body. Just so happens that the little thing in our hand does both of those jobs. We don't have to hold two objects up on the patient and get different readings from them. So we have one thing that does both jobs. Okay, so an ultrasound transducer is something that converts electrical energy into mechanical energy, and we're familiar with that mechanical energy being sound. It has a longitudinal, it's a longitudinal mechanical wave, right? So what does that mean to you? Jennifer? What's a longitudinal mechanical wave? Can you hand this back to her? Mm-hmm. What does that mean? Longitudinal mechanical? Yeah, Diana.
Isn't it just the way the waveform comes back? Because I know, like, when you were talking about transverse is this way, but it's really longitudinal, which is those lines right next to each other.
Okay.
So isn't it the way that it comes back?
Okay. So our wave travels from one point to another, our sound wave does, along a direction. Okay. It does that by vibrating molecules as it goes along, and these are little molecules here. Okay. And these molecules vibrate back and forth along the same plane as the propagation. Okay? So it's longitudinal. They're moving back and forth along this direction of the propagation. Okay? So that's longitudinal. Mechanical, it means that it has to have particles in there in order for it to transmit. Okay? A sound wave cannot transmit in a vacuum. It has to have these particles in there. All right? So give me an example of a transverse wave, Brant.
Transverse wave?
Yeah.
Is that the lake you like to
Right. A water wave, an ocean wave, sure. Yeah, the water's moving up and down, and the wave is propagating from wherever the stone landed in the pond out to the outside of the pond. Right, so very good. Okay. So poling is a way of making these piezoelectric materials. We talked last time about a little bit about piezoelectric materials. I'm going to kind of draw up here what a piezoelectric material is. So if we just have a material of some kind, and it's made up of little molecules, and each of these is going to represent a molecule, all right? And each of these molecules in our piezoelectric material has a plus and a minus charge, okay? Okay, what poling is it's simply, when they make this, it's lining up these so that at room temperature, when everything's just settled and the material is just nice and calm there, they all line up together in the same way, all right? So very simple. Now, if we take this material and we apply a voltage across here, I'm going to just call it 5 volts for no particular reason, okay? And if we make the positive side here and the negative side here, okay, so this is now negative and this is positive, okay, what's going to happen is my material in here is going to want to line up more so that the negative is towards positive, right? Opposites attract. You know that? Okay. And so it'll be very similar to what the arrangement here is, but they might be a little more vertical. They're going to try to change their alignment so that they're just like this. Okay. Now this was discovered by Pierre Curie back in the days when he was doing experiments and his wife was working on radium. Okay, so this is what will happen, is they'll line up like this. Now then, if I reverse the charge, okay, and I make this part down here negative, and this up here positive, these opposites are going to, these are the same, they're going to repel, and the opposites are going to change. So the material is going to try to flip, and it can't flip completely, so it'll start flipping this way. And you can see it doesn't really fit, so what ends up happening is it changes its shape so that you get a little longer and a little flatter, okay? And this will be positive, and now the minuses are trying to be attracted to the positive, okay? Like that. And the material kind of squeezed together. All right. So now we're going to take off our charge here and let this material go back to its relaxed state where we first found it. And in that case, we had all our molecules were at a little bit of an angle in there, just kind of hanging out together like that. Okay. So everyone feels comfortable with how piezoelectric material works? Any questions about that? We give it a charge and it actually will change shape. All right? We feel good about that? Anyone feel ungood about that? All right. Now, without giving it a charge, what happens if we physically squeeze it? What happens? Stephen? Similar. If we squeeze it, we give it mechanical energy, what's going to come out over here? A charge. Right. So if we squeeze this together, we get out of it our 5 volts. Okay? We give it enough squeeze. All right? We get back our 5 volts. So now we're putting mechanical energy into it and we're getting back voltage. All right? And if we pull on it, then we get a minus 5 volts. Right? Changing the shape one way or the other, we'll get an electrical signal back out of it. That is the piezoelectric effect, and that was discovered by Pierre Curie back in the day. I don't know exactly what year. Now, what he also found was that if you take this material and you heat it up, you put it on your skillet and you start burning it, at some point it will lose its piezoelectric properties. And all that's happening is it gets hot, and then all these molecules start rearranging themselves so that they're not in order. Okay, that's called the Curie temperature. Okay, that's one of the things you have to know about, is the Curie temperature can cause it to lose its piezoelectric properties. And the Curie temperature is one of the reasons why we don't autoclave our transducers in order to get them sterile. If we autoclave them, they get up over 200 and something Celsius, then they lose their ability to be piezoelectric materials. The other thing that happens is all the epoxy that holds them together falls off, and then you've just got a bunch of wires sticking out of your end of a, and it's really not nice. Yeah, that's exactly what I was going to say. Wires sticking out of the end of a wire. But it all falls apart. It's held together with epoxy. Epoxy will break down at about 150 degrees centigrade Celsius. The Curie temperature is maybe about 400 to 500, so it really isn't the Curie temperature we're hitting in the autoclaves, but you don't want to heat these things up is the point. They will lose their piezoelectric properties. Okay, so we talked last time about PZT, lead zirconate titanate, being the main ingredient of the historic choice for ultrasound transducers. That's still true. They do use some composite material in there to help reduce the matching layer effect. So it's not completely just lead zirconate titanate anymore, but there's some other stuff going on. Okay. Oh, wrong button. All right. The impedance mismatch, we can lower that by using the composite materials. And what those materials are, I don't know. The author of your book calls it PZT5. Means absolutely nothing to me. And I don't know. Maybe it means something to you. Have no clue. So originally transducers were these single crystal materials. They were just made out of a single piece of PZT material. And that material had a certain thickness and a certain shape to it. And that shape helped determine where the transducer would focus its ultrasound beam. Okay? So you had this one crystal, and what would happen is it was attached to a little motor. So we had a little motor here attached to it on some pulleys, and you have this thing here, and it's a motor whirling around. And that would cause it to wobble back and forth. So it would just sit there and it'd turn back and forth. And that's how we created our image with these old single crystal transducers. And that's what we have here on the this old machine is just that. I'm going to show you what the breast phantom looks like with that. And it actually isn't too bad of an image. Okay, so when we're looking at this, this is a breast phantom with a few things in it, and it doesn't look like too bad of an image. As we scan it, we can actually make out those details pretty clearly. So it's not horrendous. We can see cysts, we can see solid objects. They all show up pretty well. It looks a lot like liver tissue. Yeah, oops, wrong button. It's obviously it's a phantom. Somebody made it. It just, who knows what's in it. It certainly doesn't look like breast tissue. So it just has some things in it that appear as we scan over it. But I mean, you can definitely see that line at the bottom. It's very clearly shown. It's a nice clean interface. These are not too bad. If you ever get a chance, pull this aside in the lab in there. Take a look at your liver with it, and you might actually be surprised how diagnostic these little things are. You really can get pretty clear images with them. There's some reasons for that we're going to go over, but a single crystal, there's no interference from other crystals, and it really can look really sharp. Really, really, really. Okay. So let's go back to our the newer transducers that we have in our machines that we're currently using, these kind of transducers. These are what we call the multi-element transducers. Okay, they have, oops, I see we're not on the screen there. go back to computer and go back to whiteboard. Okay. All right. Okay, so these transducers have multiple elements in them. Some of them that we have in the lab have as many as 512 crystals in it. Yeah, and that's not even the most you can get. Nowadays you can find these with 5,000 crystals in them. So there's a lot of different things coming out on the market. Most of them, like this one, will probably have at least 128, maybe 256 crystals in the head of this transducer. Okay, so they're getting better and better about making them and doing things that will help you out. So these are electronically focused. We can actually change the focus on the single crystal, like this one. It was focused at one place. The electronic, we can focus it at multiple places, and it uses a technique called phasing, and we'll get into that probably next week, what phasing is. All right, so the piezoelectric effect is we hit our crystal with a voltage and it changes shape. We hit our crystal with sound and it produces a voltage. Very simple. Don't go too far with this, okay? It's very simple. It's just converting electricity back and forth different ways. This is the same type of thing we're showing you here. In this case, we've got a voltage across it to cause it to expand. Here we've put a voltage to cause it to contract. Here we've taken the voltage off and we've let it relax. Okay? So it's very simple how it works. All right. So I think I started talking last time about how the beam extends out from the crystal. Do you guys remember that?
So it focuses and goes back out?
Yeah, it focuses and goes back out. So we have this area from here where the beam will just naturally focus down and then it'll expand back out again. Okay, and then at a certain distance here, where it is the narrowest, we call that what? Christy? The focus, right. That's the focus. Okay. And what do we call all of the area in front of the focus? Near zone. And what do we call the area past the focus? Far zone, right. And just because they don't like us, what's another name for the near zone? Yeah, Fresnel zone. And the far zone? Fraunhofer. Named after Professor Fraunhofer at the, I don't know, pick a yeah, the Fraunhofer Institute. There you go. So at the focus, that is where the beam is the narrowest, and that's going to give us our best resolution. Okay? And because all of the energy of the sound beam has been focused into one small area, that's going to have the highest intensity there too. Okay? So the highest intensity occurs right at the focus for registry purposes. Okay? The reality is it occurs slightly before the focus because of attenuation effects. But for the registry, they're not going to take that into account. They want you to say that the highest intensity is at the narrowest area, which is the focus. Okay? All right. All right. So when we create a sound wave, and this is where we're starting to get into the little piece of paper I gave you today. When we create a sound wave, what we're going to do is send it out as a pulse. Why do we send it out as a pulse? So we can receive echoes, right? Why are echoes important? That's what we're going to create our picture with. Yeah, that's right. Okay, so let's do that. We'll go back to there. Okay. So we have our pulse that we send out into the body. Okay. And then what do we do for a while? We wait. We don't send out any more pulses. We get echoes back. Okay. After we've waited a certain amount of time, we send out another pulse. Okay? And then we wait. All right. So this period of time that we are actively sending out a pulse is called the pulse duration. And that goes from this point to this point. Okay? So when we're talking about time and pulses, we talk about pulse duration. Andrea, what do we talk about when we're talking about distance and pulses? Any idea? Okay, when we're talking about distance, we're talking about a length. Okay? So we're talking about a length, and it's actually the amount of space taken up by our pulse. So we call it the spatial pulse length. Okay? So these are measured from the start of the pulse to the end of the pulse. And if you measure it using time, it's the pulse duration. If you measure it using distance, it's the spatial pulse length. Okay, so on your pink and green sheet, you can put down this distance in the time domain, if you're measuring in time, as pulse duration. You can put down this same distance in the distance domain, or space domain, as the spatial pulse length. All right? It's measuring the same thing two different ways. Now when we send out a pulse, if I want to image 1 centimeter deep, how long do I have to wait before I send out another pulse? How long does it take for my sound wave to go from the surface of the skin 1 centimeter deep and then come back so I can hear all the echoes that will come back from that? 6.5 microseconds to go 1 centimeter deep. Another 6.5 microseconds for the echoes to come back. So that's a total of 13 microseconds to image a depth of 1 centimeter. Okay? So now I want to image a great big fat person who has a liver that's 20 centimeters deep. How long do I have to wait between sending out pulses? I have to wait 20 centimeters times 13 microseconds per centimeter. Okay? And how long is that? 260 microseconds, right? Or about 0.26 milliseconds. All right, so that's how long it takes just for one pulse to go 20 centimeters deep and come back. All right? And that's how you can calculate it. Your depth times how long it takes to do a pulse. So, just so happens they like to ask registry questions. Here's one. How long does it take for a pulse to travel 5 centimeters? To travel 5 centimeters, 5 centimeters times 6.5 microseconds per centimeter equals about what, 32.5 microseconds. Okay. Okay. Because we're just traveling there. Okay, here's another test question. How long does it take to image a structure 5 centimeters deep? Now we're using the 13, exactly. So anytime we're talking about just going that far, we're talking 6.5 microseconds. Anytime we're talking about going there and coming back, we're using 13. So they might say image to get a reflection back from a depth of sometimes. So they'll use, you have to read the questions very carefully because they really do like to use both of those terms like that and confuse you. And what we call the period of time that we're waiting to send out another pulse is called the PRP, or the pulse repetition period. Okay? And so to image 20 centimeters deep, I need a pulse repetition period of at least 260 microseconds. I have to listen that long before sending out another pulse. Okay? So if I'm listening, if I send out a pulse, if I'm right here and I'm sending out a pulse along aisle 1 here, and I send it out and I want it to get all the way back to Diana in the back there, I have to wait 260 microseconds for the pulse to come back to me. Now I can move over and send out a pulse along aisle 2. Okay? And the period of time that I have to wait for my signal to get all the way to the back and come to me is the pulse repetition period. It's that amount of time I have to wait before repeating my pulse. Okay? The pulse repetition frequency is how many times per second I can send out a pulse. So if somebody says, what is the PRF control, what do you say? How long you're waiting for the echoes to come back, that's one way to put it. Another way to put it is it controls my depth. The pulse repetition frequency controls the depth. How many times per second I can send out a signal controls how deep I can scan. If I'm only scanning 1 centimeter deep, so if I'm sending out only a pulse to the first aisle here, to the first aisle, first person, then I can send out a lot more pulses than if I have to send it all the way back to Diana in the back there. Okay? So really short pulse repetition period, okay, very high pulse repetition frequency. If I'm sending it all the way to the back, I have to have a very long pulse repetition period, and it's going to be a very low pulse repetition frequency. We want to do a demonstration?
Yeah.
It's going to be a beach ball. All right. So the frequency, the pulse repetition frequency, okay, here we go. Just toss it back, okay? Very quick. Now I'm going to go a little deeper. Okay? It takes a lot longer to image deep. Whoops, sorry. Okay, so enough of that. Okay, so you see the frequency can be very, very quick, If you're very, very shallow and the frequency is very, very long or high, or am I saying that right? The frequency is low if we're imaging deep, okay? And remember, the pulse repetition period is the reciprocal of the pulse repetition frequency, all right? We got that, okay. Now, one of the things we want to think about here is how our pulses are affecting our patient's body, the biological changes that are in effect. Now, if I'm using a short pulse duration and listening for a long time, is that going to heat up the tissue much? No. Short pulse duration, long listening time. So I send out a pulse. Every time I send out a pulse, I'm sending out energy, okay? All right, if I send out a really small pulse, not too often, how much energy have we got? Okay. Very small pulse, and we're not sending it out too often, okay? So what we're saying is our duty factor, the amount of times I have to throw this ball, is actually pretty darn low. Now, if we send out a big pulse or even a small pulse many times, so we'll do that, small pulse, and we'll send it out real fast, back and forth, okay? It's going back and forth, and what's happening is the pulse repetition period is short, so our duty factor is actually pretty high. The duty factor is defined as the pulse duration divided by the pulse repetition period. Okay? That's how much energy we're putting into the patient. We want this to be very low. Duty factor. Okay? And for those of you that have had small children, it's not the duty, duty, okay? So it's the duty factor is what we call it. And it's the pulse duration divided by the pulse repetition period. So if I increase the amount of listening time, if I increase my pulse repetition period, what happens to my duty factor? Somebody say it goes down. Samantha?
It goes down.
Thank you. Okay. If I increase my pulse duration, what happens to my duty factor? Samantha? Goes up. Okay, very good. So you got that? Good. All right. Where are we at?
Okay, you increase pulse duration, the duty factor goes up.
Yes. Yes.
And
If this part, if the numerator gets bigger, then this has to get bigger. Okay, and let me show it to you graphically, okay? This is my pulse repetition period from here all the way to here, correct? All right. Now, if I increase my pulse duration by adding more cycles, and we just stop right there, real short, almost all of my time is spent sending signals into the patient's body, and I have very little time that I'm actually listening. Okay, so a lot of energy goes in, and I just barely wait, and then I start sending a lot of energy again. Okay, so that's my pulse duration. I've increased my pulse duration without changing my pulse repetition period. So what I've done is now I'm just basically cooking my patient. Works good if they're pork chops, but so now if I decrease my duty factor, or if I want to decrease my duty factor, and I do that by decreasing my pulse duration, now I have a very short pulse duration in a very long listening period. Okay? So I haven't changed my pulse repetition period, but I've made the spatial pulse length shorter, or the pulse duration shorter, and I'm just mostly listening now. Okay? So now my patient is getting very little energy into them. which is a good thing. So biological effects, we've turned it down by keeping our duty factor low. All right? So now if we keep our normal duty factor and we increase our pulse repetition period, so instead of stopping here, I'm going to come way down here. And this is actually not drawn to scale, by the way. Okay, if I come down here, okay, now my pulse duration is still the same length, right? It's still a short pulse duration, but my pulse repetition period is a long time. Okay, so now what has happened to the duty factor? It's gone way down, hasn't it? Okay, so for biological effects, we want to keep this duty factor as low as possible. Okay? Okay. So just like when we determine what the spatial pulse length was, we did this in the lab the other day, we can determine our pulse duration. It's just simply the period of one wavelength times the number of waves that we're creating, the number of cycles. Okay? So it's the period times number of cycles. That's all the pulse duration is. How do we calculate the period? Heather? How do we calculate the period? Sure you do. Okay. Elena, how do you calculate the period? You've been reviewing chapter 1.
Yes.
Okay. Anybody?
1 over F.
1 over F. The frequency equals 1 over the period. The period equals 1 over F. Okay? If you know your frequency, you know your period. It's that simple. The PRP equals 1 over the PRF. PRF equals 1 over the PRP. These are reciprocals of each other. Okay? Frequency and period are always reciprocals of each other. Okay? So if we know our frequency, we can calculate our period. What is our frequency usually? Usually about 5 megahertz or so, right? Somewhere between 2 and 10. We like 5. 5's good. Gives us nice images. Okay. So we can calculate the period of a 5 megahertz sound wave of being 1 over 5.0 megahertz, okay, which is going to equal, what's the reciprocal of 5 is 0.2. Micro is the reciprocal of mega, and seconds is the reciprocal of hertz. So the period of a 5 megahertz sound beam is going to be 0.2 microseconds. Okay? And so if we're using, in this example here, we've got how many cycles? Heather? How many cycles have I got there? 3 cycles. So what's my pulse duration? Period times number of cycles. 0.2 times 3 0.6 microseconds will be my pulse duration for a 5 megahertz signal that has 3 cycles per pulse. Okay. So here is a slide showing you the duty factor. The duty factor is lower if the pulse duration is short. The duty factor is higher if the pulse duration is longer. And this is just restating the same thing that we talked about, spatial pulse length. It's a way of measuring the actual length of the pulse. Okay. I don't think I want to get into creating a frame, but when we make a frame, an image on our screens, we're just sending out one pulse, in the simplest case, one pulse per line of image. Okay? So I want to make an image of this room. I send out a pulse here. I get 1, 2, 3, 4 echoes back. And I would just put that on my... Oh, that's a terrible sector. Here we go. Put the curve down there. There we go. So we put the first one in and we get 4 echoes back. I move over one spot. I send out a pulse. I get 1 echo back. I move over another spot. I get 3 echoes back. Each time I'm sending out a pulse. Skip 1, 2 here. Okay, then I come over and I send out a pulse. I don't get any echoes back. That's fine. We leave that part blank. We come over here. We send out a pulse. We get 4 echoes back. Okay, so you see how I'm making an image of the room in a sector shape as I just go around and I send out pulse and wait for the echoes to come back. Okay? So we just, for each line of scanning, gets 1 pulse in the simplest model. Yes?
Why isn't it all reflected back from the first point? Why does it go past it to 81 for instruments?
Because when we get a reflection back from an interface, some of it, some percentage is our reflected percentage of our signal comes back to us. Some of it is the transmitted, continues on. We call that the transmitted percentage. Okay, so at every interface that we get an echo back from, part of it comes back to us, part of it keeps on going. Okay? So we're fortunate that not all of it is reflected back. So when I send out my echo along here, I do get some back from my first interface, but the rest of the signal keeps on going. Okay? So the question being, why don't we get all the echoes come back? Because of the reflection and transmission. At each interface, some of it's reflected, some of it continues on and is transmitted. Okay. Yes?
So when it reflects the first time, then it loses a little bit of energy, and then it goes and so on.
Yeah.
And loses more every time it hits something.
Yeah. Yeah, and so by the time we get to that liver that's 20 centimeters deep, we're looking at the back wall, we've lost a lot of energy. We've lost a bunch of energy. Yeah.
So that's why we have to use lower frequency transducers to get the depth.
Well, we use lower because the lower the frequency, the less attenuation. Remember, we talked last time about attenuation, and it's related to frequency. So we lower our attenuation, we lower our frequency, we don't get as much attenuation. So we get more transmits on into the back of those big patients. Yeah. Yeah. Okay. So now we've talked all about pulse wave imaging. This is kind of your drawing that we're going to be creating over the next few weeks. A period is the length of one cycle, of course, the length in time. The length in space of one cycle is the wavelength. The wavelength we can calculate, it's C over F. Period is 1 over frequency. Pulse duration is equal to the period times the number of cycles. Spatial pulse length is the wavelength times the number of cycles, so they're very equivalent. You can see they're just drawn in different domains. We have the time and we have the distance domain here. Our duty factor is defined as the pulse duration divided by the pulse repetition period. And that pulse repetition period controls what? Stephanie? What does the pulse repetition period control? Yes, you do. I know you know. Depth, correct. Controls depth. I erased it. Okay. What does the pulse repetition frequency control? Jessica? Depth. Depth, yeah. These are the same thing. Pulse repetition period and pulse repetition frequency are the same thing. They're just mathematical reciprocals of each other. So if you can control one, you can control the other. It's very simple. Okay. Now, I'm going to step on off of this for right now, even though I know you guys are frantically writing down, but you don't have to, because we're going to come back to it again and again and again. And we're going to fill out that drawing until you know it perfectly well. Okay, so I wanted to talk a little bit about the matching layer, because this was in your homework this week, bandwidth and sensitivity before we quit for the day. And this is going to be very simple. Matching layer, optimal matching layer is the wavelength divided by 4. Your book went to a lot of trouble to make it sound real complicated. Wavelength divided by 4 is the matching layer. If they ask you about the matching layer on the exam, you have to know that it's the wavelength divided by 4. That's about it. And what it does. What does it do?
Gradually decreases the impedance.
Right. It allows us to jump over 12-foot walls, doesn't it? One step at a time. How many of you in here live in a 2-story house? About 4 or 5? How many of you in a 2-story house jump from the first floor to the second floor every day? I take the steps. They're my little impedance matching layers. That's all they are. Okay, sensitivity. Your book, I think, says that sensitivity is not defined. Well, that's a bunch of bunk. Sensitivity is defined. It's the ability of the ultrasound machine to detect weak signals. Okay? You can also think of it as its ability to distinguish between the weakest signal and the strongest signal it gets back. Now remember, Heather's point that a lot of the signal is reflected back instead of being transmitted is true. And when we get the echo coming back from the back of the class and it's trying to get back up here, it also has to go through all of those interfaces on its way, right? And so by the time it gets back up here, it's a very, very weak echo. Very, very weak. And so our machines have to be extremely sensitive in order to detect those. And it turns out that they are. They have a sensitivity in the range of about 160, 120 to 100, I think we'll just say 120 decibels. And if you don't think that's a lot, it's a ton. That's a tremendous sensitivity. And we're going to talk about how that works. Now, bandwidth is sensitivity. Okay? And you don't have to write this down, but just think for a second here. Our ears hear things at different frequencies better than others, right? Okay? This was the whole purpose of bringing the noise machine in here today. So if I play this note, if I turn this on and play this note, let's see, is it on? There we go. Okay, so that's a very low note. We can hear that very well with our ears, okay? Now if I play a much higher note, you can still hear that pretty well, but it does fade out quicker. It's harder for our ears to pick up. And if I go much higher, it would be even harder for our ears to pick up. And some of us can't even hear high frequencies. So I'm going to play those two notes together. And Christy, you're the farthest away, so you tell me when you hear the first note disappear, okay? Okay, right there, she lost the first note. Can you still hear the low note, though? It's still going. Sensitivity. Our ears are much more sensitive to different frequencies, okay? There was your concert for the day. Yeah, I know. It's the worst concert you've ever been to. So that is where we get into bandwidth. The transducers are just like our ears. There's no difference. They hear things too. And some frequencies they hear better than others. And that's all bandwidth is that it can hear certain frequencies better than others. Okay, next time when we come in here, we'll talk more about bandwidth. We'll draw up all kinds of things on the board that describe bandwidth. And then you'll be like going, oh, God, that's awful. And there's, guess what, some equations that go with it. It's called center frequency and Q factor. And we're going to make them really, really simple. Okay? So it's going to be real simple. Yeah? Question?
Well, because they're in for number 12 and 13, and it's just confusing in that they don't really show the stuff.
Okay, so questions 12 and 13. I worked out 10. Somebody had a question on questions 10 and 11 earlier today. I worked those out and posted them on Blackboard. So I'll work out 12 and 13. I'll try to put up a explanation that makes sense.
Okay.
Okay?
Thank you.
All right.